All right, everybody, so what is going on? Phil here with another video. Wanted to let you know that my new course has finally gone live. That is what I've been working on for the last month and why I have not made any YouTube content. So you get 5.5 hours of content that teaches you how to read, interpret, analyze, and implement deep reinforcement learning papers. We're going to implement deep Q learning, double deep Q learning, and dueling deep Q learning, all from scratch using the source papers, nothing else but source papers and Pytorch. If you don't know anything about reinforcement learning, it's not a huge problem because I have an entire module, about an hour of content set aside specifically for that, where you will code a Q learning agent from scratch, just from first principles. You really only need high school mathematics and a basic understanding of deep learning and a willingness to learn. So I only have two favors to ask. First of all, if you are going to purchase, if you decide you want to purchase, please use the link provided. Otherwise, Udemy takes half the credit. And two, if you do purchase a course, they will prod you for a rating right after you buy the course. Regardless of what rating you give it then, once you've taken some portion of the material and have an accurate assessment of the quality of the course, please leave an honest review for other students to know what they are buying. So I'm going to include an entire module here on YouTube as a promotional video, as a thank you to all of my YouTube subscribers and viewers. And you can also click the link down below to head to the course landing page to check out other free modules from the course. I'll also include a link down in here to the GitHub where you can see the code for the course, so you can see what type of stuff you're going to be coding. You can get an idea of how it is structured. And I'm quite pleased with the results here. This is 5.5 hours of content, a fairly enormous undertaking for me. I know you're going to love it. Go ahead and check it out, and I'll see you in the course. In the previous lesson, we learned that all agents face a fundamental dilemma. Do they expand their knowledge of the environment at the expense of a short-term loss in reward, or take the best known action? There are a number of strategies for dealing with this dilemma, and we're going to rely on epsilon greedy. This is a strategy that balances exploration and exploitation before settling on a mostly exploitative strategy. Recall that the value function is the estimate of the expected future rewards given that the agent is in some state and follows its policy. This process of exploration and exploitation helps the agent to refine its model of the environment and gradually approach the true estimate of the value function. Each time the agent samples a state and receives a reward, it can update its estimate using a formula of the following form: new estimate equals old estimate plus some step size multiplied by the quantity, target minus old estimate. Now, this target is aptly named as it is in the direction in which the agent is moving its estimates. It can be noisy and have a high degree of uncertainty, but it is generally assumed to be the right direction to be moving. In the simplest case, the target is precisely the reward the agent is given at some time step. We'll have to modify this later, but the basic idea is that it is a term proportional to the future rewards the agent expects to receive. The next parameter we want to look at is the step size. It controls how quickly the estimate changes for each step. In practice, it can have many forms, and this can have a big impact on whether or not the agent converges on some accurate estimate. Functional dependencies, including 1 over n, such that it approaches 0 as the estimates get more accurate, are possible, but we're going to use some constant but small value. The frequency which this estimate is updated varies based on the class of algorithms. For instance, in Monte Carlo algorithms, another type of model-free reinforcement learning, the estimates are updated at the end of each episode using the returns that follow each time step t. Remember that the returns are the sum of the discounted rewards. These returns are the target in the prior equation rather than just the reward. Q-learning, on the other hand, is in the class of what we call temporal difference learning algorithms. Here we are going to update the agent's estimate of the value function at each time step rather than at the end of the episode. This means that Q-learning is a sort of online algorithm that can learn in something approximating real time rather than sitting around and waiting to learn. It's also well suited for non-episodic tasks, meaning tasks that never really end in an episode due to this online nature. In temporal difference learning, our update for the value function is of the form v of s at time t equals v of s at time t plus alpha times a quantity r sub t plus 1 plus gamma times v of s sub t plus 1 minus v of s sub t. Since the equation has terms that are proportional to the estimated time t and the time t plus 1, we are effectively using one estimate to update another estimate. This makes it what is called a bootstrapping algorithm. One may ask, is that really a good idea? What if we start out with bad estimates? Garbage in, garbage out, right? Well, not quite. As long as we have a fixed policy pi and the step size parameter is sufficiently small, these estimates actually converge to the true values so long as we sample each state enough times. The definition of enough is a bit fuzzy right now, but it should be of order hundreds or more. The more times the better, but a dozen times isn't really going to cut it for most cases. Okay, so then I've convinced you that the value function converges, but how can we use this in Q-learning? Way back in the video on value and action value functions, I also talked about action value functions, which tell us the value of state and action pairs. It's this quantity we want to use rather than the value function. Don't worry, the update equation is similar to what I just showed you, but there are some differences. The action value function is denoted by Q, and we update it according to the following equation. Q of S and A at time t is equal to Q of S and A at time t plus alpha times a quantity R sub t plus 1 plus gamma times the max over actions of Q of S at time t plus 1 for all actions minus Q of S and A at time t. There are a few things to note here. First, we've just swapped out Q for V and included the fact that it's a function of both state and action. Second, we are taking a max over actions for the Q value for the next state as part of our update equation. We'll talk more on that in a minute. For the frozen lake environment, there are only a small number of states and actions. This means we can represent this action value function Q as a table. Each row is a state, and the columns are the actions, with the entries being the value for that combination. This is an example of what's called a tabular learning method, because it uses a table to keep track of the states and actions the agent has visited. So for each state the agent finds itself in, we're using an epsilon greedy policy to choose actions. Look up that state in the table and check out the estimates for all the possible actions. If you're taking a greedy action, then take the action whose entry is highest for that state. If you're taking a random action, well, pick one at random. Use a reward to plug into the above equation to update the Q table and then just repeat the process. After playing enough episodes and not resetting the table between episodes, the agent will sample each state and action pair enough times to get an accurate estimate. Another thing to note here before we get to the full Q-learning algorithm we want to implement. We are using an epsilon greedy strategy to pick actions, but we are updating the estimate for Q based on the purely greedy action. We are using one policy to update an estimate for a completely different policy. This is what is called off-policy learning. There are also on-policy learning methods where we use the same policy to update the action value function as well as to choose actions. The on-policy temporal difference learning method is called SARSA, which is an acronym for state, action, reward, state prime, and action prime. We won't be implementing it in this course, though we'll see it mentioned in one of the papers later on. If you'd like to learn more about it, you can check out my YouTube channel for some examples. Okay, so now we have all the vocabulary out of the way and we are ready to take a look at the full algorithm to implement. Start by initializing Q for all states and actions in the state and action spaces. This is arbitrary, except that as always, the terminal state is by definition valued at 0. Initialize a learning rate alpha, discount factor gamma, and random parameter epsilon. Repeat for each episode. Initialize the starting state. Repeat for each step of the episode. Choose an action A based on the current state S using an epsilon greedy strategy in Q. Take your action, get the reward and new state. Plug the reward into the update equation to update the estimate for Q. Set the old state to the new state. That's really all there is to regular Q-learning. Let's implement this and finally conquer the frozen lake environment. But before I cut you loose, I'll give you some pointers on how to structure your solution. The agent should be represented as a class which has a Q table, learning rate, discount factor, and epsilon. You'll need class functions to initialize the Q table, choose actions based on the current state, as well as learn given an input of a state, action, reward, and new state. It's easiest to represent the Q table as a dictionary with states and actions as keys. You also want to decrease epsilon over time to some minimum value. I also recommend putting the agent class in a separate file from the main loop, as this is considered coding best practice. The output for this should be a plot that shows the running average of the past rewards for the past 100 games. This is known as a learning curve, as an overall upward trend in the average reward over time is a clear demonstration of learning by the agent. You can also print the running average and episode number to the terminal every 1,000 games or so, just so that you know it's running. Let the agent play a large number of games, something like 500,000. Pause the video here, work on your solution, and come back to hit play when you're ready to see my solution. Alright, now that you've had a chance to code it on your own, let's take a look at my solution. Our imports are going to be relatively light with just NumPy. As instructed, you should stick the majority of the functionality in the agent class. Our initializer is going to take the learning rate, gamma, number of actions, number of states, epsilon start, epsilon end, and epsilon decrement factor. And of course, we want to save all of those parameters as member variables of our class. Now our QTable gets initialized as an empty dictionary, and then we'll call a specific function to initialize the QTable. As stated in the instructions, the initialization for each state and action pair is arbitrary except for the terminal state, which must identically be 0 for all actions. Now since it's arbitrary, we may as well set everything equal to 0 for all state and action pairs. Now that we've finished initializing Q, we are free to handle the functionality for choosing the action. Of course, choosing the action will be a function of the current state of the environment, and we're going to use epsilon greedy. Just as a refresher, epsilon greedy means we're going to calculate a random number. If that random number is less than epsilon, then we're going to choose an action at random. If that number is greater than or equal to epsilon, then we will find the maximal action. All we've done here is use a list comprehension to create a list of integers in the range of number of actions, and use NumPy random choice to choose one at random. Now what we've done here is use a list comprehension to create a list of elements corresponding to the action values for the given state by looking up the relevant quantities in our QTable. Then we're going to use the NumPy argmax function to find the index of the maximal action from that list. Now there is a caveat here. The NumPy argmax function has the built-in behavior that when two elements have a tie, it will return the index of the lowest element. So that means if action 0 and action 1 have the same Q value, it will always return action 0. Probably a better way to do this would be to write a custom function that breaks ties randomly, such that half the time it chooses the lower index and half the time it chooses the higher index. We'll see that it doesn't really matter, but it's just a way to improve upon my solution. And of course, in either event, you want to return the action you chose. Next, we can turn our attention to the decrement epsilon function. Now, I chose to decrement epsilon linearly. You can use a 1 over square root dependence. You can use a logarithmic or exponential dependence. It's not really critical. I'm just going to use linear, so if your solution is different, it doesn't matter so long as it decreases epsilon down to the minimum value over time. Alright, finally we come to our learn function. This will take the state, action, reward, and new state as input. We're going to want to calculate the maximal action for the new state of the environment, and then use that in our update equation for Q. And of course we want to decrement epsilon at the end as well. Now, of course, all of the same caveats as above in the choose action function apply to the argmax here for the amax. So this is just the update equation for Q. We're incrementing it by learning rate multiplied by reward plus gamma times the Q value for the next state and maximal action, and subtracting off the value for the current state and action. Next, we have to handle the decrement epsilon. Now, of course, you could argue that you can handle the decrement epsilon in the main function. I've chosen to stick it here just to adhere to the principles of object-oriented programming, by which I mean that the main function really doesn't need to know how the agent handles decreasing its own epsilon. Either way, as long as it works, it's good, but I've just done it this way to be a little bit more consistent with OOP. Alright, let's head to the main function and write up the test loop for this. Now our imports are going to be a little bit more heavy duty here. We're going to need gym, pyplot, numpy, and our agent. So let's start with that. And of course, we want to start with initializing our environment as well as our agent. Now I've chosen a set of defaults. These aren't written in stone. These are simply what I chose. If you use different values, that's okay, so long as we end up getting a similar result. So I'm going to pick a learning rate of 0.001, a gamma of 0.9, an epsilon n of 0.01, and a rather slow epsilon decrement factor. And of course, we need an empty list to keep track of our scores and win percentages. And as instructed, we'll want to play 500,000 games. And at the top of each game, we want to reset the done flag, environment, and set the score to 0. And simply play each episode. Of course, we start by selecting an action, taking that action, learning from the new observation, action reward, and old observation tuple, increment our score, and set the old state to the new state. And of course, at the end of each episode, we want to append the score to our list. And every 100 games, we want to calculate the win percentage for the previous 100 games. And every 1,000 games, we want to print our debug information. And at the end of all the games, we want to plot our win percent list and show it. Okay, now that's done. Let's head to the terminal and see how it works. All right, here we are. Okay, so I forgot the self dot in the QLearning file. Let's go ahead and change that. So that was line 37, which is right here. Self dot in actions, save. And let's make sure I didn't do it anywhere else. Here is good. All right, let's head back to the terminal. Let's try again. And it is running. So I'll let this run for a minute and then I'll show you the results when it finishes. Alright, that is finished running. You can see an overall upward trend in the agent's win percentage over the course of the games, and it tops out around 70% average with some win rates over 80%. If you were able to achieve a comparable score, congratulations. Let's head back to the lecture. Just to recap, temporal difference learning is a type of online learning. It bootstraps by using one estimate to update another. QLearning is a tabular off-policy learning method that uses an epsilon greedy policy to update the estimate for the purely greedy policy. By implementing a QLearning agent in our frozen lake environment, we were able to achieve a consistent 70% win rate, which is a massive improvement over our paltry 20% rate from earlier in the course. In the next modules, we're going to talk about what to do in the case of continuous state spaces.